This is Rank Over Class, the Untapped Potential of Ranking in Natural Language Processing. Text classification has long been at the forefront of natural language processing, with applications across sentiment analysis, online content tagging, and others. However, text classification by nature suffers from a variety of common challenges that prevent meaningful impact. Such challenges include text ambiguity, dataset imbalances, and many others. In this work, we argue that many of these challenges can be addressed by replacing classification with ranking. Our proposed ranking pipeline consists of two main components: a transformer encoder and a context aggregating multi-layer perceptron. The two input passages are first passed through the transformer encoder, and the resulting feature representations are concatenated and passed through the multi-layer perceptron to produce two values subsequently used to rank the input passages. Effective and stable training is enabled by means of a margin-based ranking loss with strong representation learning capabilities. The efficacy of our claims are tested using 4 publicly available datasets. Our first dataset, extracted from the Stack Exchange forum, provides an excellent opportunity for evaluating our approach. The main objective here is to assess the quality of answers given to questions posted on the forum. We randomly select 250,000 posts from 6 communities and more than 17,000 users as our training dataset. Ground truth labels describing post quality are based on the number of votes an answer has received, normalized by the number of votes its corresponding question has received. One would expect text classification to be a plausible solution under these circumstances. However, experiments show that as there is no shared context connecting the passages, classification models fail to perform beyond randomly guessing. Just as a human observer cannot objectively assess the quality of a random answer without knowing anything about its context, classification models fail similarly. This is where contextual pivot points play an important role. By grouping passages based on some shared context and training a different classifier for each separate group, the problem can be solved. However, by reformulating the problem as ranking, we can solve the problem using a single model. As such, we group passages based on the users that posted them and extract passage pairs for training. There are about 8 million such pairs in our dataset. The results evaluated using common ranking metrics are very promising. A very interesting application of this is tracking the skill level of users over time. To evaluate this claim, we create a random test set of 50 users with at least 20 answers each. The model is well capable of accurately sorting the posts from a user based on their quality without having access to any information other than the text of the posts. By referencing these results against the time the passages were posted, we can track and predict changes in the skill level of any given user. The next dataset used in our experiments is the Amazon Fine Food Reviews dataset, where the objective is to predict the sentiment of product reviews. With around 500,000 reviews from 250,000 users about roughly 75,000 products, this dataset is highly challenging due to its class imbalance. All reviews are labeled from 1 to 5, with 1 denoting the most negative and 5 the most positive sentiment. Once again, we use classification to establish a baseline. Since this dataset is more contextually coherent, classification yields reasonable results, but a ranking model can perform even better. We perform ranking with the contextual pivot points being the users that posted the reviews and the products the reviews are about in 2 separate experiments. 2 separate test sets are thus created accordingly. The model is capable of near-perfect ranking in both experiments. An interesting observation is that the models trained to perform user-based ranking converge faster. This is due to the fact that the writing style of a user is a stronger cue for the model to learn. The most challenging dataset in our experiments is a collection of tweets about self-driving vehicles. This dataset contains nearly 7,000 tweets labeled from 1 to 5, with 1 being the most negative and 5 the most positive. This dataset is extremely unbalanced, with more than 60% of the data belonging to one class and about 1% to another. In this experiment, we attempt to directly compare ranking and classification results. A balanced test set is thus created by randomly selecting 100 tweets from each class, and the ranking results are converted to class labels to enable a direct comparison. To do this, we first sort all the passages in the test set using our ranking model. The sorted tweets are then divided into 5 equal segments and assigned labels from 5 to 1. Note that this conversion is not necessary in any real-world applications and is only performed here for an easier comparison. Since our approach is not a classification one, we cannot use common metrics such as F1 or area under the curve. But since the testing dataset is perfectly balanced, accuracy provides an excellent measure of performance. Results show that ranking can significantly outperform classification by up to 22%. We also test our approach using a well-known information retrieval dataset called the MS Marco, despite the fact that information retrieval is not the focus of this work. Due to hardware restrictions, we use less than 1% of the available training data and the smallest form of our transformer networks. In spite of this, our approach remains competitive with dedicated information retrieval techniques. While this work demonstrates how ranking is a better fit for many classification problems, this is not universal. Certain problems, such as categorizing text by topic for instance, will still require a classification solution. Ranking provides a relative comparison of 2 data points and cannot assign absolute values. For example, our approach can compare 2 movie reviews to predict which is more positive, but it cannot determine whether both reviews are positive or negative. This can be addressed in the future by means of a double-headed model capable of classifying and ranking at the same time. Additionally, using a list-wise ranking approach rather than a pairwise one can lead to better and more accurate results with fewer post-processing requirements. This was Rank over Class: The Untapped Potential of Ranking in Natural Language Processing. Thank you.